Hello. The purpose of this video is to demonstrate a Carry-Lookahead adder. This is a 3-bit Carry-Lookahead adder. I just got tired of wiring, I'll admit. Plus, the bigger the Carry-Lookahead adder, the harder it was probably to explain. I copied this schematic from the Wikipedia article. I have tried to label things in a similar fashion as that article so that you could kind of match up what I've done here against the article. This is obviously not a compact circuit. This is for demonstration purposes. The Carry-Lookahead was actually developed quite a long time ago when it was realized that the ripple adders are slow. If you have to rely every time on the carry to propagate through various gates, as say there's a bunch of carries in an addition, all those carries need to propagate, and then you have what's called like gate delays. And the gate delays, the more gates you have to go through to get the answer, the longer it's going to take to get an answer. So that's the purpose of the Carry-Lookahead, is to sort of look ahead and figure out what the answer is going to be kind of in parallel, so you don't have to go wait for all of these carries to ripple through the system. So this is the front end. There's only 3 bits being added here. These 3 switches in front are for A. These 3 switches in front are for B. So I'm going to add A to B. If you look at my labels here, A0 and B0 is in the first unit here. The second unit is A1 and B1, and the third is A2 and B2. And there's a display for those bits here, plus a carry bit. Okay, so the front is simple enough. It is basically, 3 half adders, 1 for each bit. Now, these pins here, I guess I didn't get them all labeled, but we'll just look at this one here. C0 is the carry 0 that is propagated all the way through the circuit. Well, we don't have a carry input for 0. I mean, that would be if we were cascading a couple different adders together, like building 2 4-bit look-ahead adders. I could transfer the carry from one to another. Okay, so there's, but I just, sort of faithfully copied again, the schematic from the Wikipedia. So G0 and P0 are the propagate signals. The Wikipedia article explains this in a little detail. It's it takes a little work to think through this, but the propagate bits are basically coming off the XOR here of the half adder. And that means that the propagate is basically the sum of like A0 and B0. The sum of A0 and B0 is coming off that XOR gate. So that is the propagate signal. And the G, the generator signal, is coming off the AND gate, or the carry, from the first half adder there. Again, you can bring up the Wikipedia article to see the schematic. Maybe you can kind of see how those propagate bits. Now, if you look at my schematic here, you'll see the XOR output here for the first half adder goes into the P0 signal, and the second one goes into, if you can see that, the G0 signal, the generate. So that's all that happens on the front side. So let's go to the back. And now what I have here, each board here with the XOR gate, that's the second part of the half adder circuit. And that that adds some very specific signals, plus the carry out from the previous bit. So this is bit, this is bit 0, this is bit 1. Bit 1 the final XOR here for the full adder is coming from two sources. One, the CarryLookahead, and the second is the P1 signal. And it's a little hard to understand why all this is without going through all of the math, but the math works. So all these generate and propagate bits. When they're all added together in the correct way, you get a more efficient adder. So I just made it to make it kind of obvious. I just drew all these wires all the way across, even when they're not being used. So let's just look at the first bit here. So again, this is the second half of the half adder, the XOR gate, which will give us our output. And to get that, we add in carry 0, which is always 0 in our case, and we add in the output of the sum of the first half adder, which is our P0, our propagate 0 signal. That's what I was explaining over here. The what I call the sum, which is done with the XOR, it goes to the P0 signal here. And then that's it, and that actually outputs our first bit. And then this board here, this in-between board, is basically our CarryLookahead computation. For the first bit, it's fairly simple. If you look at the Wikipedia article, you'll see that there's an AND gate going into an OR gate. And that AND gate is taking the C0 signal and the P0 signal, and it's ANDing them together. And then it passes it on to the OR gate. And the reason why we don't have an OR gate is because this game doesn't have OR gates, it has pins. I should point out a pin is not exactly like an OR gate, and I could show you just to show you really quickly. I put a buffer in here because otherwise it didn't work, because the signal was allowed to go backwards, which was causing problems. So pins are not exactly OR gates for that reason. Okay, so going back again to the discussion of the first CarryLookahead computation, the first CarryLookahead computation has an AND gate on the carry 0 signal and the propagate 0 signal, and then there's an OR gate that is the OR between the G0 signal and the output of the AND gate. And it's a little hard to follow all that, I'll admit, but that is kind of the first bit. And then after that, it just keeps getting more and more complicated. And there's actually kind of a pattern. I think if you were to go to the Wikipedia article and kind of write this out, it might help you understand this better. In the video comment, I'm probably going to put what the AND gate is specifically, because those are the most complicated parts of the circuit. There is going to be one or more AND gates. The first CarryLookahead computation uses one AND gate. The second one uses two. The third one uses three, and it just gets more complicated as you add bits. And there's kind of a pattern, and again, I'll put that in the comments for the video. So, it's, without going into exhausting detail about all this, it's a little hard to kind of explain without visuals of the Wikipedia article. That's why I keep referencing it, because you can go look at that article and you can see a schematic, and if you just carefully write down all those lines, you can kind of see how it all comes together. I'm just going to demonstrate it here. So if I add, let's say, 3 plus 3, the answer is 6. And C3 plus C6. There's a carry bit on. That looks like a flaw in the circuit. I thought I tested all this. Let me just, so adding 1 is fine, 1 0 is fine, 1 1 is fine, 4 is fine. But yeah, that's funny. 3 plus 3, it should just be 4 and 2. So, but it is very tricky to get this exactly right. I just happened to pick one case that didn't work correctly. Let's say I had 4 and 4 and I get 8, and that's correct. All these first 3 bits are 0, and the carry is 1, as it should be. Then if I add another 1 to that, now I have 9. If you think if the carry is my 4th bit, you could see that, and then 10, etc. Okay, well, I won't just continue playing around with switches there, but hopefully that gives you a little bit of an idea of how you can kind of build this. If I were to do this again, I would try to make it considerably more compact, but this was for a demonstration and for my own attempt to understand the signal flows better. Thanks for watching.